Okay, in the second part of the two-part series on rubidium-strontium decay, I want to consider how we can solve the problem we identified in the first part. Remember, the problem was that in many, in fact, most rocks, the amount of strontium-87 that we measure in the rock includes a certain amount that was present in the rock before radioactive decay took place. So if this was the initial condition of the rock shown by the blue dot, it undergoes radioactive decay like we know it does, moving off to the upper left with a slope of -1. Amount of rubidium-87 drops, amount of strontium-87 increases, and the age of the rock is proportional to the length of this line. The problem, age, right? The problem is that we don't know where it started from because we don't know the initial concentration of strontium-87 in the rock. And without knowing that, we can't know the age of the rock. So how do we get around that problem? Well, in practice, what we actually, first thing we do is we divide both the x-axis and the y-axis, the rubidium-87 radioactive parent on the x-axis and the the strontium-87, the radiogenic daughter on the y-axis. We divide that by a stable daughter isotope. And in this case, we divide it by strontium-86. Now, when we do this, it's the same amount of strontium-86 on both the x and y axis, so we're not actually changing anything in the way we interpreted that diagram before, right? So as radioactive decay happens, the parent ratio here is going to decrease because rubidium-87 is going to decrease, and the daughter ratio is going to increase because strontium-87 is going to increase. And so if this is my composition, initial composition on this ratio diagram, as the rock ages, it will once again move up to the upper left with a slope of -1 as the ratio of rubidium-87 to 86 strontium decreases and the ratio of strontium-87 to strontium-86 increases. So all the kind of interpretations that we did before are exactly the same, except that we're using ratios. And we're doing that, by the way, because it turns out it's easier to measure strontium-87-86 ratio than just to measure one of those isotopes all by itself. So we divide both sides by the common stable daughter isotope, strontium-86. Okay, now in order to sort of figure this out, one of the key ideas is going to be that we have to think about where does rubidium and strontium actually go into the rock. Remember, rocks are made up of minerals, and so the question of where those elements go into the rock can be turned into where do those elements go into the minerals. And as an example, let's imagine a rock that only consists of 3 minerals: quartz with a formula SiO2, potassium feldspar, sometimes called K-spar, with a formula KAlSi3O8, and a pyroxene with a formula CaMgSi2O6. And these are the only 3 minerals in the rock, and so these are the only 3 places that can host rubidium or strontium. Now, rubidium and strontium are actually elements that are not very common usually. They're known as trace elements. That means they're elements that are so scarce that there aren't enough of them to make their own minerals. And so the only place that they can go is they can sneak in to some other mineral that generally doesn't have that. That's not supposed to have rubidium or strontium in it, but can accept it under if the fit is acceptable. So what we have to consider then is chemically how easy is it for the ions rubidium and strontium, these are the ions that we're talking about, how easily can these ions be incorporated into these 3 minerals? Well, remember, the minerals have sites where the different ions in the mineral go, and those sites have very strong preferences for the type of ions they want to see. Now, rubidium and strontium are actually pretty unusual. They're both pretty large cations, and rubidium especially is a really large cation. So for most minerals don't have a place where they can put a really large cation like rubidium or strontium. However, rubidium and strontium are similar enough to 2 elements that are actually already found in 2 of these minerals, and that is potassium and calcium. Rubidium with a +1 valence charge is actually pretty similar in size. It's a little bit bigger, but not too much bigger than potassium, which also has a +1 valence charge. So it turns out that any kind of mineral that can readily accept potassium, like K-spar, will have no problem accepting a small amount of rubidium substituting for potassium. So that kind of substitution of rubidium for potassium is easy. Similarly, strontium with a 2 plus charge is actually not too different in size and identical in charge to calcium with a 2 plus charge. And so minerals that already have a place for calcium 2 plus can usually accept some amount of substitution of strontium 2 plus for the calcium because those two ions aren't too different. On the other hand, a mineral like quartz doesn't have any place to put either of those two large cations. And so in general, quartz is going to be like, no way, there's no way I can fit either of you guys into me. And quartz will in general not have any or very, very, very tiny amounts of rubidium and strontium in it. So because of the substitutions of rubidium for potassium and strontium for calcium, K-spar tends to concentrate rubidium because rubidium can substitute for potassium, and pyroxene tends to concentrate strontium because strontium can substitute for calcium. So if we look at our three minerals again, the only three minerals that are going to be in our rock, we can predict that quartz is going to have none of either of them in it. K-spar is going to have a lot of rubidium because it can substitute for potassium, but relatively little strontium because it doesn't have calcium in it, and therefore it's going to have a high rubidium-strontium ratio. Pyroxene, because it contains calcium, is going to have a lot of strontium, but not much rubidium because it doesn't contain potassium, and it's going to have a low rubidium-strontium ratio. So now imagine what happens when these rocks are getting made out of these three minerals. And the key idea is as rocks are being made, not all the rocks are going to have exactly the same proportions of quartz, K-spar, and pyroxene. Some of them are going to be a little enriched in K-spar, some of them are going to be a little enriched in quartz, etc. And the rocks, as the proportions of the minerals in the rocks change, so does the concentration of rubidium versus strontium. So for example, a rock which is enriched in K-spar is going to be enriched in rubidium relative to strontium, and that rock is going to have a high rubidium-strontium ratio. On the other hand, when it comes to incorporating different isotopes of the same element, that is strontium-86 versus strontium-87, rubidium-86 versus rubidium-87, those two isotopes of the same element behave chemically identically. That is to say, when potassium is growing and it says, okay, I can take a little bit of rubidium because rubidium's close enough to did I say K-spar? When K-spar is growing and it says I can accept a little bit of rubidium because rubidium is similar enough to potassium, it just grabs whatever rubidium it finds. It doesn't know the difference between rubidium-86 and rubidium-87. They're identical to it. Similarly, when pyroxene is growing and it's grabbing a little bit of strontium as a substitute for calcium, it doesn't care whether it grabs strontium-87 or strontium-86. They're identical to it. There is no distinction chemically between strontium-87 and strontium-86. And what that means is that the ratio strontium-87-86, rubidium-87-86 in the three rocks is going to be exactly the same as it was in the magma. There is no reason why a mineral growing will prefer one isotope of potassium over another isotope of potassium, or one isotope of strontium over another isotope of strontium. So in this example, let's imagine that three different rocks form. Because they have slightly different proportions of those three minerals, they're going to have different rubidium-strontium ratios. The rock that had a lot of K-spar in it had a lot of rubidium in it, and it's got a high rubidium-strontium ratio. That's the rock over here. Oops, right over here. And the rock with a low proportion of K-spar in it is kind of a relatively little amount of rubidium in it, and it's the rock over here, and it's going to have a low rubidium-strontium ratio. And remember, because when these minerals are growing from the magma, they absolutely don't care about strontium-87 versus strontium-86. It's all the same to them. They're going to have exactly the same strontium-87-86 ratio in all three rocks. So they're going to plot along the same horizontal line because they have exactly the same strontium 87-86 ratio, but they have different enrichments of rubidium relative to strontium. So that's the trick of this isochron method. At the same time, 3 different rocks form that have different ratios of parent to daughter, rubidium to strontium, but identical strontium 87-86 ratios, identical initial daughter ratios. And now let's see what happens when these 3 rocks age. We know already what happens. We talked about this with 1, right? As the rock ages, it's going to move off to the upper left, slope of -1. It's going to lose rubidium and gain strontium like that, right? And that's going to happen for every one of these. So let's go back to our example with 3 and see what happens. So here we have 3 different rocks, different proportions of minerals, so they have different rubidium-strontium ratios. That scatters them about the x-axis, but they have identical initial ratios of strontium 87 to strontium 86. And we're going to let these rocks age. And as they age, they each move in a slope of -1 to the upper left, with the rocks that are more enriched in rubidium 87 moving farther away, such that a line drawn through all of the final compositions will intersect the y-axis at the point of the initial strontium 87-86 ratio. We call that line an isochron line, and that is the basis of the isochron dating technique. Now, notice that the age of the rocks is proportional to the slope of the isochron diagram. If we were to let more time elapse, right, this isochron line would rotate to steeper and steeper angles. Therefore, the steeper the isochron line, the older the rock. In other words, initially it's got a slope of 0. That's the isochron line. Initially it's got a slope of 0. These rocks are 0 years old. And as they age, they follow compositions that define an isochron line that gets steeper and steeper and steeper. So the idea here is that the steeper the isochron line, the older the rock. So let's sort of summarize with what you actually would do to use this technique. You go out in the field, you find some kind of pluton, some kind of igneous body, and you notice that all the rocks are genetically related to each other, but some have slightly more of one mineral than another, and that's good. You want to collect a bunch of different rocks with slightly different rubidium-strontium ratios, right? So you pick these rocks that you think will have slightly different rubidium-strontium ratios. Then you go analyze the rocks for rubidium and strontium 87 and strontium 86. And then you plot those data up, and this is what you get. This is the final plot, right? So how do you get the age now? Well, notice what you do now. Then you fit the isochron line. The isochron line should go through all your data, and it will intersect the y-axis. There's the isochron line. It'll intersect the y-axis at your initial concentration of strontium 87 to strontium 86. That initial ratio of strontium 87, 86. And then from that, you can back out where the initial compositions must have been before radioactive decay took place. They must have all lain along this line. And the age, remember, is proportional to the length of the green, red, and blue arrows, or the slope of the isochron line. And so through techniques which are really straightforward, you can determine the age of the rocks. And the interpretation, therefore, is that at some point, all the rocks, 3 rocks, lay along this line in the big circles. And then after time passed, they evolved to represent the final positions, the ones that you actually measured today in your laboratory. And that to swing that isochron line from horizontal to this level of steepness requires a certain amount of years, a certain number of years. That is the age of the rock. So what does that age actually mean? So if you determine the age of a rock, let's say an igneous rock, it's 105 million years. What happened 105 million years ago? What you're actually dating, remember, the starting point was when these different mineral compositions got arrayed along that line. And that corresponds to the time when the minerals formed from the magma. In other words, when the magma solidified. So once those minerals have solidified, once they've solidified, they then will start to, the the rubidium in those minerals will start to decay, and that will change the concentration of rubidium in the minerals and strontium in the minerals, and that then is when the clock starts. The clock starts for an igneous rock when the rock cools to the point where minerals form. In other words, that's what we typically take to mean the time when an igneous rock formed. And that's what in general we're going to be using this technique for, that to date igneous rocks to find out the time when the igneous rock formed, when it stopped being a liquid and became a solid.